This is section 1.3, part A, measure center. We're going to look at the mean and the median. The most common measure of center is the ordinary arithmetic average, also known as the mean. To find the mean, which in statistics class we're going to call x bar, it is this x with the little line over top of it, we call x bar. So the mean of a set of observations, add their values and divide by the number of observations. If the n observations are x1, x2, and so on, then we would add those all together and divide by n. We can also write x bar as the sum of your x sub i's divided by n. So if we refer to the data on travel times to work for a sample of 15 North Carolinians, we need to find the mean travel time. So from this stem plot, we can see that the first person has a travel time of 5, the next one is 10, 10, 10, 10, 15, 12, the next one is 12, then we have 15, 20, 20, 25, 30, 30, 40, 40, and 60. And we know there are a total of 15 observations. So the numerator would add together to give you 337. We know there are 15 observations. So this will give us 22.5 minutes as the average. Calculate the mean again, this time excluding the person who reported a 60-minute travel time. So we know that the original total was 337. We are taking away the person who traveled for 60 minutes, and that's going to give us a new total of 277 minutes. Now, instead of having 15 observations, we only have 14 observations. And if we divide that out, that'll give us a 19.8 minute average. So as you can tell, by just removing one potential outlier, we drastically change the mean of our data set. So the mean is very sensitive to influence of extreme observations. There may be outliers, but a skewed distribution that has no outliers will also pull the mean towards its longer tail. Because the mean cannot resist the influence of those extreme observations, we say that it is not a resistant measure of center. A resistant measure of center is a statistical measure that is not affected by, or only affected in a tiny bit, by outliers or data that is not roughly symmetric. The mean tells us how large each observation is in a data set if all of the data sets were equally split among the observations. So this is kind of like a fair share. So if we were to collect everyone's marbles and redistribute those marbles so that everyone has the same amount, the amount that each person has would be the average. The next thing we're going to look at is the median. We're going to represent the median by a capital M. This is the midpoint of a distribution. The numbers such that half of the observations are smaller and half are larger. To find the median, you're first going to arrange all the observations in order by size from smallest to largest. If the number of observations n is odd, the median is just the center number in the list. And if you have an even number of observations, that median is going to fall between two different numbers. So you will have to find the average of those two values. Medians require little arithmetics, so they are easy to find by hand for small sets of data. Arranging even a moderate number of values in order is tedious, however, so finding the median by hand for large sets of data is very unpleasant. So if we look at the travel times for the 15 North Carolinians to work again, and we arrange them in order from smallest to largest, we know there's 15. So if we have 7 observations to the right and 7 observations to the left, we know half of 15 is 7.5. So it has to be the 8th value would be the median. So 20 would be the median of this data set. Now we can also look at people in New York State who have travel times. Because of the heavy traffic near the city, their travel times are longer. What do the data say? Are their travel times actually longer than North Carolinians? So we took a random sample of 20 New York workers. We need to make a stem plot of the data. Be sure to include a key. So the shortest time on this list is 5. The longest time on this list is 85. So when we create our stem plot, we'll have to go from the tens position of 0 all the way up to 8. Now there are no 70s, but we still can't skip that spot. So with a tens position of 0, we only have 5. Of a tens position of 10, or tens position of 1, we have these data values. So we have 1, 2 tens, and we have 4 15s, in the 20s, we have 3 20s, and we have 25. We have 2 30s. We have 2 40s, and we have a 45. We have 2 60s and a 65, and then we have that 85. Now, if we need to make a key, we can say 6/5 represents a travel time to work of 65 minutes for a New Yorker. Again, in your key, you need to put it back into the context. We need to find and interpret the median. So to do this, the first thing you would need to do is put, again, the values in order from smallest to largest. Because there are 20 data sets, we know 20 divided by 2 is 10, exactly 10. So we need to have 10 data values to the left. We need to have 10 data values to the right. We need to find the one in between there. So we need to find the between 10 and 11. Since the 10th data value is 20, the 11th data value is 25, we would add those two values together and divide by 2, and we would get a median of 22.5 minutes. When you're comparing the mean and the medians, the mean and median of roughly symmetric distributions are pretty close together. If the distribution is exactly symmetric, the mean and the median are exactly the same. In a skewed distribution, the mean is usually farther out in the long tail than the median. The mean and median measure center in different ways, and in both are very useful. Don't confuse the average value of the variable, the mean, with the typical value, which is described as the median. For data sets that are roughly symmetric, the mean and the median are both indicators of the center. But because the mean is not a resistant measure of the center, it is affected by skewness and outliers, so it is pulled in one direction or another. The mean, on the other hand, is a resistant measure of center, So for data sets that are skewed or have outliers, the median is a better measure of center. So if a data set is symmetric, you can use the mean or the median. But if a data set is skewed or has outliers, when discussing the center, you should use the median. Here, once again, is the STEM plot of travel times to work for 20 randomly selected New Yorkers. Earlier, we found that the median was 22.5 minutes. Based only on the STEM plot, would you expect the mean travel time to be less than, the same as, or larger than the median, and why? So if we look at this STEM plot, we can see that the data is going to be skewed to the right or skewed towards the larger numbers. Because it is skewed, we know that the mean and the median will not be the same because the mean is not resistant. The mean will always be pulled towards the longer tail or the direction of skewedness. So since this is skewed to the right, we know the mean will be farther to the right than the median. So the mean will be larger than the median. Use your calculator to find the mean travel time. Was your answer to question 1 correct? Remember, when you're finding mean, you will add all the data values together and you will divide by the total number of observations. If we do this, we will get an average time of 31.25 minutes, which is larger than the median, which was 22.5 minutes. Remember, when you are comparing two quantities, you do need to say which is larger, which is less than. We need to interpret your results for question 2 in context without using the words mean or average. So, if we divided the travel time evenly among all 20 people, each would have a 31.25 minute travel time. So this is without using the word mean or average. We can say if we distribute the times evenly among all the travelers, they would each travel 31.25 minutes. Would the mean or the median be more appropriate summary of center of this distribution of travel times? Justify your answer. Since this data set is distributed to the right, it is skewed to the right, we would be better off to use the median because the median is resistant to skewness and outliers. The mean is being pulled to the right because of the skewed right distribution.